Good morning, students. Welcome back to Signals and System online video lecture series. I hope all you are safe being in the home and you done very well in the exam. So, from this class onwards, I am going to continue our class that is in Signals and System by reviewing the whatever the things we have studied in the third unit so far. I'm going to cover the remaining syllabus of the signals and system. Third unit is about the continuous time signal analysis. In this unit, we are going to study particularly Fourier transform. That means Fourier transform is a mathematical tool which is used to analyze the continuous time signals, and that can be continuous time signals can be converted into the frequency domain signals by making use of the Fourier transform. In completely third unit, we are going to study the Fourier transform, and in case of second unit, we have studied the Fourier series. In the second unit, we have studied the Fourier series, but it is applicable to only periodic signals. That means the Fourier series is having some limitation. It can be applicable to the periodic signals which repeat periodically over the time interval minus infinite to the plus infinite, then that signals are called as the periodic signals. So it cannot be applied for non-periodic signals such as aperiodic signals, we may call it as. In case of signal that is there in the time domain, it is a way of analysis of the signal with respect to the time. In the time domain, the signal or function value is known for all the real numbers for the case of continuous time, or at the various separate instants in the case of discrete time. So now we are having the two things. One is in case of Fourier series, and that can be applicable for the periodic signals, and that signal is about the time domain signal. In time domain signal can be represented with the time, and it is for the case of continuous time at the various separate instant in case of discrete time. So now by making use of the Fourier transform, we can convert the continuous time signal into the frequency domain. Continuous time signal into the frequency domain signal. That means the time domain will be converted into the frequency domain, and the Fourier transform can also be applicable for the aperiodic signals. That means Fourier transform can able to overcome the limitation of the Fourier series. Fourier series can be applicable to the only periodic signals, whereas the Fourier transform can be applicable to the periodic signals as well as aperiodic signals. So one more important thing of the Fourier transform is that Fourier transform converts the time domain signal into the frequency domain signal. Time domain signal is a one in which all the amplitude of the signals can be represented with respect to the time. Whereas in the frequency domain signal is nothing but all the amplitude signal behavior we can study with respect to the frequency. So the analysis of a signal far more convenient when it is represented in the frequency domain. Very, very important point. When the signal is represented in the frequency domain, that is very, very far to analyze the signal when that is represented in the frequency domain. So that is the importance of the Fourier transform. For the two things we are looking for the Fourier transform, one is about the One is about the we can apply the Fourier transform to the aperiodic signals also, where these aperiodic signals cannot be analyzed by making use of the Fourier series. And the next important point to be noted in case of Fourier transform is a mathematical tool which converts the time domain, that is x of t, time domain signal into the frequency domain signal. That means what? When the signal is represented in the frequency domain, it is more convenient to analyze that particular signal, so that the Fourier transform is converting the continuous time signal into the frequency domain. That means what? Time domain signal into the frequency domain signal, so that due to these two reasons we are going to have the Fourier transform, and that can be used to analyze the continuous time signals. Then these two are the necessity to study the Fourier transform. Now I am going with the standard formula for the Fourier transform. In the previous classes I have explained how the time domain signal that is converted into the frequency domain signal. Now let assume x of t. X of t is a time domain signal. It is a time domain signal. That means what? The signal behavior can be studied with respect to the time. Signal behavior can be studied with respect to. So let assume x of t is a time domain signal in which the signal can be represented with respect to the time. That means what? We can study the signal behavior with respect to the time. And now this time domain signal can be converted into the frequency domain signal. Let assume that frequency domain signal is x of omega. Omega is nothing but it is an angular frequency, where t is nothing but the time, so that x of t is a time domain signal, whereas x of omega is nothing but it is a frequency domain signal. So now x of t, I have the x of t, it is a time domain signal on which I am applying the Fourier transform. That is a mathematical tool which converts the time domain signal into the frequency domain signal. This is the x of t on which we applied the Fourier transform. Then we can get the frequency domain signal, that is x of omega. To achieve the Fourier transform of any time domain signal, this is the standard formula. Anyway, derivation of this particular equation we have discussed in the previous classes. Now x of t is a time domain signal on which we applied the Fourier transform, so that we got the frequency domain signal. So that x of omega is nothing but it is a frequency domain signal, and the frequency domain signal we got this one by applying the Fourier transform on the time domain signal, so that is nothing but x of omega is equals to integral minus infinity to plus infinity x of t into e to the power of minus j omega t dt. That means what? To have the Fourier transform of x of t, this is the standard formula, where x of t is a time domain signal and on which we applied the Fourier transform. That is nothing but integral minus infinity to plus infinity x of t to the power of minus j omega t dt. Then the resultant will be it is a frequency domain signal, that is x of omega. Then this omega is nothing but what? It is an angular frequency. Then if you wanted to convert that is into the normal frequency, that you can write x of f is equals to integral minus infinity to plus infinity x of t into e to the power of minus j. Omega can be replaced by the 2 pi f into the dt. So that mostly we can make use this formula to convert the time domain signal into the frequency domain signal, or in other words we can tell that to have the Fourier transform, to obtain a Fourier transform of any time domain signal, we will be using the standard formula, that is x of omega is equals to integral minus infinity to plus infinity x of t into e to the power of minus j omega dt. Then if we are having the frequency domain signal, if you wanted to convert that is into the time domain signal, this is nothing but it is called inverse Fourier transform. Fourier transform will convert the time domain into the frequency domain, whereas inverse Fourier transform will convert the frequency domain into the time domain. That means what? We have the x of omega, it is a frequency domain on which we are applying the inverse Fourier transform, so that we will be getting the signal that is a time domain signal, that is x of t. The further the formula is x of t is equals to, that means what? On the x of omega, it is a frequency domain signal on which we will be applying the inverse Fourier transform, so that we are getting the time domain signal, that is x of t is equals to 1 by 2 pi integral minus infinity to plus infinity x of omega into e to the power of j omega. And if you convert that into, if you are having the signal in the normal frequency domain, so that if you wanted to find the time domain of corresponding that signal is equals to, it is nothing but integral minus infinity to plus infinity x of f into e to the power of 2 pi f into t. These are the two standard formula, and from this we can have the conversion of the time domain signal into the frequency domain signal, or frequency domain signal into the time domain signal. Now I am going with the one of the important statement. If I have the x of t on which I am applying the Fourier transform, we are applying the Fourier transform, so that we can get the frequency domain signal. And if you are having the frequency domain signal on which we are applying the frequency domain signal on which we are applying the again Fourier transform, but that is inverse Fourier transform. If we apply the inverse Fourier transform, obviously you can get the x of t, so that this representation of Fourier transform is called as Fourier transform pair. It is called as Fourier transform pair, because from this representation we can tell that if you are having the x of t on which we applied the Fourier transform, so that we got the x of omega, it is a frequency domain signal. And now we are having the x of omega, it is a frequency domain on which we are applying the inverse Fourier transform, so that we can get the time domain signal. So this is another way of representation of the Fourier transform. We are having the x of omega, it is nothing but a frequency domain signal. How can we get the frequency domain signal? By applying the Fourier transform on the x of t. X of omega is nothing but Fourier transform applied on x of t. Next one is what? If I wanted to have the x of t is equals to, it is a time domain signal, x of t is equals to inverse Fourier transform of x of omega. And like this we can describe, describe the Fourier transform. Now I am going to explain the one of the important thing that can be used in giving the solutions of some of the problems in case of Fourier transform. So now we are going to study the magnitude and phase representation of the Fourier transform. After calculating the Fourier transform of a particular time domain signal, that is x of t, we can get the Fourier transform, that is x of omega. After knowing the x of omega, we must able to find out the amplitude and the phase angle. We must calculate after knowing the Fourier transform of the given signal. The magnitude and the phase representation of the Fourier transform is the tool used to analyze the transformed signal. Now these two can be used to analyze the transformed signal. Transformed signal is nothing but it is a frequency domain signal. By making use of this magnitude and the phase angle, we can easily analyze the that is frequency domain signal. So now the general x of omega is a complex valued function of omega, and we can have that complex value of x of omega. This is the form of the Fourier transform we can achieve for the x of t. We have the x of t, that is a time domain signal, on which we applied the Fourier transform, so that we got the x of omega. X of omega is a complex valued function of omega, therefore x of omega is equals to xr of omega plus j into xi of omega, where this is nothing but it is the real part of x of omega. This is a real part of x of omega. This is nothing but imaginary part of x of omega. This is a real part of x of omega, and this is imaginary part of x of omega. We know x of omega, actually we know x of omega. From that, xr of omega is nothing but it is a real part of x of omega, and this is imaginary part of x of omega, and from that we can calculate the magnitude. Magnitude is nothing but modulus of x of omega is equals to under root of real part square plus imaginary part square. This is modulus of x of omega is equals to, that is square root of x square r of omega plus xi square r of xi square of omega. This, by making use of this equation, we can calculate the magnitude, and the phase angle can be given as angle of x of omega is equals to tan inverse of xi of omega. That means what? Imaginary part of x of omega by the real part of x of omega. So now I'm going to conclude this review of the Fourier transform. First one, when the signal is in time domain, it is difficult to analyze the signal, so that we are converting the time domain signal into the frequency domain signal. The point is noted here. If a signal is there in the time domain, it is very difficult to analyze the time domain signal, so that we are converting the time domain signal into the frequency domain signal. First point. Second point is that when a signal is a aperiodic signal, that can't be described, that can't be analyzed by making use of the Fourier series, so that can be analyzed by making use of the Fourier transform. So that due to these two reasons, we are using the Fourier transform. In short, we can call FT. So after applying the Fourier transform on x of t, we will get the frequency domain signal, and after applying the inverse Fourier transform on x of omega, we can get the time domain signal. So after knowing the transformed signal, that is about the frequency. After knowing the frequency domain signal, we require to calculate the magnitude and the phase angle. We have to calculate. So then this is a x of omega. After calculating the Fourier transform, we will get that is x of omega is a complex valued function of omega. Then we can have from that we can calculate the magnitude. And the phase. Magnitude can be calculated modulus of x of omega is equals to square root under root of xr square of omega plus xi square of omega, where xr square of omega is a real part of omega, and xi square of omega is a imaginary part of omega, and phase angle is angle of x of omega is equals to tan inverse of xi of omega by xr of omega. This is about the things we have to calculate in the Fourier transform of a given signal. Now we need to plot after knowing the phase angle and the magnitude. We have to plot the two things. One is about amplitude spectrum, and another one is about phase spectrum. Amplitude spectrum and phase spectrum. Amplitude spectrum is nothing but it is a graph between the magnitude, that is x of omega, to x of omega versus omega, that is called amplitude spectrum. And phase spectrum nothing but it is a plot between the phase angle, that is angle of x of omega versus omega. This is two things we need to plot. One is amplitude spectrum. It is a plot between the magnitude of x of omega versus omega is called amplitude spectrum. The plot of angle x of omega versus omega is known as it is a phase spectrum. The amplitude spectrum and the phase spectrum together called as a frequency spectrum. If we plot the two things together, if we plot the amplitude spectrum and the phase spectrum, we can call it is a frequency spectrum. It is a frequency spectrum because the signal is represented. Now the plots are with respect to that, whatever the graphs we will be plotting with respect to the frequency only, so that is called as a frequency spectrum. It is called as frequency spectrum. In next class I am going to talk about some of the important things, such as Dirichlet conditions we are going to study. That is nothing but existence of Fourier transform. That means what? To which signals we can calculate the Fourier transform, and what is the limitation of Fourier transform we are going to study. That is in the Dirichlet condition. Next one I am going to talk about some of the important signals, as we studied some of the basic signals such as unit step signal U of t, that a ramp signal R of t, impulse signal del of t. Along with them we are going to study some more important signals such as sync signal, signum function, rectangle function, triangular function, then Gaussian functions. The 5 more functions we have to discuss, so that after knowing all these signals we have to calculate the Fourier transform of those signals. Fourier transform is a mathematical tool which is used to convert the time domain signal into the frequency domain signal. Fourier transform is used to can be applied for the periodic signals. In the Fourier transform we have to calculate the magnitude and the phase, and after that we have to plot the amplitude spectrum and the phase spectrum, and the amplitude spectrum and the phase spectrum combinedly we can call as a frequency spectrum. So students, in the next class I am going to cover the very important thing, and from that we can expect the direct questions in the external examination. So don't miss the classes, and find the free time and go through the previous classes whatever I have explained in the signals and system. Signals and system is one of the beautiful subject. If you understand clearly, then don't waste the time and be on the preparation for the next mid exams, that is second mid exams, and as well as you are going to have the external theory exams for this semester very soon. So don't waste the time, dear students. Thank you.